Welcome back. We just finished talking about confidence intervals in the previous segment, and now we'll talk about hypothesis testing, which is a closely related idea. We want to ask a question about a specific value of a parameter, like, is that coefficient 0? And in statistics, that's known as hypothesis testing. So hypothesis testing is a test of a relationship between, it's a test of a certain value of a parameter. In particular, here, the hypothesis test we'll make is that parameter 0? Is the slope 0? So what's called the null hypothesis is that there's no relationship between x and y. In other words, beta 1 equals 0, right? That's the equivalent statement. The alternative hypothesis is that there is some relationship between x and y. In other words, beta 1 is not 0. And beta 1 could be positive or negative. Okay? So mathematically, this corresponds to beta 1 being 0 as the null hypothesis, beta 1 not equals 0. Okay? So that's often the question you want to ask. That's usually the first question you want to ask about the predictors. So to test the null hypothesis, we form what's called a t-statistic. We take the estimated slope divided by the standard error. This will approximately have a t-distribution with n minus 2 degrees of freedom, assuming that the null hypothesis is true. Now, what is a t-distribution? You don't have to worry too much about that. It's basically, you look this up in a table, or nowadays you look in software or compute it for you. It's basically a normal random variable, except for small numbers of samples. N is a little bit different. In any case, you ask the computer to compute the p-value based on this statistic. P-value is the probability of getting a value of t at least as large as you got in absolute value. Okay? So for the advertising data, using, again, just TV, here are the results. Here are the slope and intercept of that line. We saw the least squares line. Standard errors. Here are the t-statistics. That's just the coefficient divided by the standard error. The one we care most about is for TV. The intercept isn't really very interesting. That's telling us what happens, what's the sales when the TV is 0, TV's budget is 0. But the one we care most about here is this guy. So this is measuring the effect of TV advertising on sales, and the t-statistic is huge. Okay, it turns out in order to have a p-value of below 0.05, which is quite significant, you need a t-statistic of about 2. We're at 17, so it's very, very significant. So the p-value is very, very small. So how do we interpret this? It says the chance of seeing this data under the assumption of the null hypothesis, so there's no effect of TV advertising on sales, is less than 10 to the minus 4. So it's very unlikely to have seen this data. It's possible, but very unlikely, under the assumption that TV advertising has no effect. Our conclusion, therefore, is that TV advertising has an effect on sales, as we would hope. Okay? So we've seen how to fit a model with a single predictor and how to assess the slope of that predictor, both in terms of confidence intervals and hypothesis test. Now, I did want to add one thing that's important. So we've seen the hypothesis test, and before that we saw confidence intervals. There's actually a one-to-one correspondence. In other words, they're doing equivalent things. To be more precise, if the hypothesis test fails, in other words, if we reject the null hypothesis and conclude that beta 1 is not 0, as we did for TV advertising, correspondingly the confidence interval constructed for that data, for the parameter, will not contain 0. Conversely, if the hypothesis test does not reject, so we cannot conclude that TV advertising has an effect, its slope may be 0, the confidence interval for that parameter will contain 0. So the confidence interval is also doing hypothesis testing for you, but it's also telling you how big the effect is. So it's always good to compute confidence intervals as well as do hypothesis tests. So for example, here we see the interval doesn't contain 0. Furthermore, we see that a lower limit on the effect of TV advertising is 0.042, which we can interpret as, these are in $1,000 units, that we're going to affect sales by 1,000 times. Oh, so for every 1,000 change in TV advertising, we'll get a corresponding change in in sales. So this tells us not only is the effect 0 or not, but how big is the effect likely to be. Okay. So where are we now? Let's see. So we've talked about how to assess the slope of an individual predictor. How about the overall fit of the model, the accuracy of the model? Well, what we can do here is we'll take the residual sum of squares. Remember, this is the quantity that we minimized in the first place to get the best estimates of the intercept and slope, the least squares estimates. So we'll take what's called the mean squared residual and take the square root. This is the average squared deviation that we achieve using the least fitting line, where this is the residual sum of squares. And we'll compute what's called the R squared, or the fraction of variance explained. And here it is. It's the total sum of squares minus the residual sum of squares over the total sum of squares. So what is this conceptually? Well, if we didn't fit a model at all, if we forget about TV advertising, and just use the mean of sales as the prediction, that's sort of the simplest prediction you can imagine. This would be our error, right? Here's our prediction, here's the true sales. So this is the no model error. And now the residual sum of squares of the fitted model is RSS. This is how much, it's going to be lower than this guy, right? It's going to be lower because we could always achieve this guy just by choosing a slope of 0. So since we've done least squares, we've optimized over the parameters. We know that RSS will be less than TSS. But this quantity measures how much did we reduce the total sum of squares relative to itself. Okay? And here it can be written in this way or this way. So this is the fraction of variance explained. And it can be shown algebraically this is actually equivalent to the squared correlation between x and y. Right? So this is simple correlation between the predictor and the outcome. Kind of makes sense, right? That the higher the correlation, the more that we will explain the variance. And there's actually an exact algebraic relationship that the squared correlation is equal to this fraction of variance explained. So what do we get for our data? The R squared is 0.61. Here it is. So in other words, using TV sales, the budget, TV budget, we reduce the variance in sales by 61%. So that's a very strong predictor. The F statistic we'll talk about in a few minutes. It's also a measure of how well the overall model is doing. So, this is quite impressive. In business and some kind of physical sciences, we see R squares like this. In medicine, we don't tend to see R squares. You might see an R squared of 5%. You might get excited. So one has to remember the domain to sort of to have a judge of how good an R squared is. But this is an impressive R squared, which you see sometimes in business and finance applications. So that completes our discussion of regression with a single predictor. In the next section, we'll move on to the harder problem where we have multiple predictors and we do a multiple regression.